Thank you for the nice introduction, Professor Tang. So it's my great pleasure and honor to make a presentation here. And yeah, I'm Jongsun Park from Korea University, and the title of my presentation today is Accelerating Transformers through Low-Wise Clustering and Transposable Computing Memory. So before we talk about the transformer architecture hardware, let me introduce my university. I'm from Korea University. So Korea University is in the northern part of Seoul. We have about 1,500 faculty members and 10,000 graduate students. And so it is very near to the downtown, northern downtown of Seoul. And in our lab, we have about 20 students. And we are mostly working on deep learning accelerator design and application, and also the embedded memory design, like SRAM and the DRAM, SRAM and the MRAM, and also processing in memory. I know that the companies and schools are very good at the designing the accelerator and computing memory. So it's my great pleasure to present here. So my presentation today is a twofold, is how we can design, we can make a trade-off, the computational complexity and the accuracy, the efficient way to make the trade-off. And second one is actually the computing memory. So how we can speed up and increase the utilization and reduce the latency of this deep learning, the acceleration. So let's talk about the first topic, the transformers. As you guys all know that transformers are widely used, and previously used the CNN extract the local features, and the transformers extract the global features, thanks to attention computation. So as Professor Myung told, the attention computation is very important. And so in case of CNN, they use very local filters, small filters, and many channels. So it goes to deeper and deeper. So the input dimension, the data is growing as it goes to the deeper layer. But in case of transformer, it has very iterative structures. So input and output dimensions are same, and output comes to input, and it goes to the iteration. So if you go to, as you know, I know that you guys are familiar with the transformer, the architecture, but let me just go over it. So if we have like a three-word sentence, I love pizza, then this sentence, these are the tokens, so which is notated as n. So n is a 3 here. And in case of GPT-3, the n limit is 4,000, 4K. And it is going to be increasing in GPT-O and later version, but it is not open yet. So I can say about the GPT-3. And the D model is how many dimensions they need to represent one word. So in case of GPT-3, they use a D model is of 12K dimensions in here. And if we go a little bit detail, after the token and the D model input is generated, it goes to the QKV generation matrix. So QKV generation matrix has a D model by D model. So if we take a look at this WQ matrix, I told you that D model is a 12K, and if it's a 32-bit, and one WK needs 576 megabyte. And we have the 3 matrix, and we have a lot of layers. So these are all the parameters. And after this input is multiplied by all this WK, finally we can get the QKV matrix. So QKV matrix is actually the input-dependent matrix. And to get the attention, they compute the QK transpose, multiplication, and softmax, we get the attention. This is very important attention. And it is multiplied by V matrix, and we can get the Z. And this dimension is the same with input, so we go to the iteration. And in case of the ChatGPT-3, the number of iteration layer is 96. Now the number of layer is going to be increasing, abruptly increasing. So we have a lot of iteration on here that's all about the transformer computation. So you guys know that how large is the matrix. and how is the computational complexity is so huge. So that's the reason that GPU are usually used to make a computation. So if you implement this transformers using the computing memory, usually the computing memory is like weight all the stored in the memories, and input is applied and get the ADC in here. But the problem is computing memory, usually the computing memory is input is applied in here and output is accumulated to the vertical way. But the problem on this QKT matrix on here is they need to QK and transpose, and both are the input-dependent metrics. So we cannot use the conventional, the non-volatile memory processing in memory. We need the write operation and transpose operation to do it. There's a huge headache in here. And so as I showed, the number of parameters are abruptly increasing. Number of parameters meaning that each layer of this, the WQ, WK, and WV matrix, it goes up huge. And I told you that attention matrix is very important, attention. And so many research works try to reduce the computational complexity of this transformers. So probably this pattern work is make attention important, so only consider which attention maybe is more important than others. And this work is make a sparse attention-based computation. So today I'm going to introduce the very simple method how we can reduce the computational complexity of this attention map. So one of the interesting observations, this work is about shows how we can just make a trade-off, efficient trade-off between the accuracy and computational complexity. So one of the interesting observations here is, let's say that we have this is a picture of a delicious pizza. So we have about n is 8, n is 8 word. And one of the interesting observation here is if the meaning of this word is similar, then it has a similar attention map. So that means if it is this picture and pizza has a similar meaning, that it shows the similar tokens, then it shows the similar attention region. Then our idea is how about we just cluster it and use the centroid value instead of computing all this. So that's the main idea. So we propose the algorithm to simplify it and also design hardware to accelerate it. So actually I will not go all the details, but if you talk about the algorithm, there is a clustering phase and centroid attention phase and cloning phase. So in the clustering phase, we need to find the clusters, how many clusters we are going to use. So, but for the attention computation, until we just finish the computation of attention, then we cannot get the result how many clusters we need. So we first reduce the dimension of matrix. It reduced about 20%. And first get the initial centroid value. And using the centroid value, we try the similarity matrix. And finally, make a clusters. So similar attention map has a similar clusters. So, okay, for each of these clusters, we used only one attention value, so we can reduce the computational complexity. And of course, to apply this, we need to store all the index numbers and what is the cluster we are using. I said that we need the index store. And then we can just compute only the centroid values, which is the clustered values, and we can reduce the computational complexity. So attention complexity is going to be significantly reduced. But finally, so the Z computation is about the computational complexity reduced to about 15%. But as I told you, the size of the Z is the same with the size of the input. So we need the restore matrix dimension to make a Z as the same dimension with the input. So one note here is if you're using the very low number of clusters, then the computational complexity is reduced a lot, but we have a higher error. But if you're using the high number of clusters, then the error is going to be reduced, but computational complexity is also not very good. Complexity reduction is not very good. So we did a simulation and find that with the less than 1% accuracy degradation, if you're using only the 15% of computation, we can just achieve the better accuracy degradation compared to previous work. And also, Bayesian transformer is more sensitive, so it has a little bit more accuracy degradation. So basic idea here is, as you know that, okay, if the input word has a similar meaning, the attention map is going to be similar, so we can use only the central values in it to reduce the computations. Of course, we have accuracy degradation, but it can be a very good trade-off method to trade off the computational complexity and accuracy. So we also designed the hardware. So each of the centroid and distance and cluster allocation can be hidden inside this, so we don't have any performance degradation. So we designed it as a 28 nanometer technology, and finally found that compared to the edge GPU and the edge CPU, we have like this, the speed ups. And compared to other previous works, we have a speed up and energy efficiency. So this is my first topic of the first talk. It shows how we can make efficient the trade-off and how we can just cluster it. Okay, so let me move on to the second topic of the computing memory. So I will go very briefly talk about the overview and move on to some interesting idea about the transposable digital SRAM computing memory. So as you guys all know that the computing memory is very actively researched. I know that Professor Sonu doesn't like it, but computing memory is very active research area. And so the reason the people are interested in computing memory is to access the DRAM. The energy is huge compared to the computation in here.
I like you.
Thank you. If the open memory access is very expensive compared to the computation inside the chips. So then the basic idea of computing memory is, because of this traffic is a huge bottleneck in here, how about just do the computation in the memory and reduce the traffic? So there are a lot of research works on running on this computing memory, especially in SRAM, and on the non-volatile memory. Computing memory is ReRAM, MRAM, and FERAM is actively researched. And also the DRAM computing memory. Actually, DRAM computing memory is most effective way to reduce the traffic. And Korean companies, they are focused on DRAM, so they're interested on DRAM computing memory. So if you go over it, the DRAM computing memory, actually Samsung just used the HBM, and base die, they're using the compute to reduce the memory traffic. And SK Hynix, they proposed the AI memory, and they added the dedicated multiplier and adders inside using the DRAM process. So it is going to be a little bit slow, but using the DRAM process to do the computation. So yeah, Korean companies are interested in DRAM, the computing memory, but the problem is in school is we don't have a DRAM process. So most of people working on the SRAM, the computing memory. In SRAM computing memory, there are two different, the analog computing memory and digital computing memory. Analog computing memory is accumulation, is the current summation on this bin line. So they sample it in the IDC. And digital computing memory, after they generate the partial product, they use the adder trees to accumulate it. But in this analog computing memory, the hardware overhead of this ADC is huge. And in this digital computing memory, hardware overhead of this adder tree is very large. This is 5 times larger than this memory array. So they have also the overhead. And also there are many non-volatile memory, computing memory. So like a ReRAM, MRAM, it is actively researched. They also have an analog computing memory and digital computing memory. And so recent research trend is, first, about 5 years ago, many people are focused on how we can just design a very good macro analog computing, one macro, 128 by 128, 64 by 64 computing memory. They focus on it. But now these days, they're using this processing element. They just implement about 16 by 16 of these macros, and they add the controllers, and they make one accelerator to run it. So these are the huge chips. And huge chips are actually presented this year in the ICC and also the architecture, the communities. So in this computing memory, let me just introduce the interesting work. This is a work by Jongsun from Cornell Tech. And what he's trying to do is he just designed one accelerator using the processing unit element, which is all the multipliers and adders. And he also designed all the computing memory, the arrays. And they want to compare it, which one is going to be energy efficient. And because he's working on computing memory, he wants to put more emphasis on it, I guess. So the result is, it is published in 2003 Micro, and they show that the computing memory, the energy efficiency is way better than the processing element. But actually, it is dependent on what kind of data set they are using, what kind of network they are running. And also, the very important one is because they have a lot of computing memory arrays. The problem is this 16 arrays is not running at a time. Some of the computing memory macros are taking rest. They're waiting the data to come in and need to provide the data to other processors. So utilization of this computing memory macro is very low. So these days, of course, they are making this accelerator in many research work. Their focus these days is how to increase the utilization of this computing memory macros. So today, I'm going to introduce one simple idea to increase the utilization in this computing memory. So as you're familiar that if you're doing the matrix multiplication, then to compute this matrix multiplication, one of the way is this input is applied on this horizontal direction, and they are added in the vertical direction to get this output. So this is this kind of matrix multiplication they're doing, right? So this is the computing memory architecture. But as I told you that in transformers, there are QKT, this transpose operation. So this is not this conventional computing memory process. Actually, if you just represent it, then this is a multiplication of QKT. So they multiply this number and this one. So they need to multiply this one and this one, get these numbers. And also, on this transformers, they're using the AV, the multiplication. So AV multiplication is also the same with the matrix multiplication, but the transpose, the operation is needed. So to execute this QKT operation in computing memory, what they need to do is, after K is generated, they need the transpose buffer to transpose this matrix, and they need to do the computation. But while they're doing the transpose operation, the utilization is going to be very low, and then that is an issue for the low utilization. So our idea is, how about we can just make a computing memory that can execute this way of the normal matrix multiplication, or we can also, if we can just matrix multiplication like this way, this matrix multiplication, if we can support both of the operation, then it is going to be very efficient, and it can be very flexible to increase the utilization of this computing memory macro. So how we can just make it? We added the switches and the 4 switches in computing memory. So we can apply the input in this direction, or we can apply the input this vertical direction as well. So, on this matrix, normal matrix multiplication, we apply the input in the horizontal way, accumulate is a vertical way, so we can execute the common multiplication. And also, the other operation, input is applied and accumulation in the horizontal way, then, okay, sorry. This is actually the chat window. And we can just support this actually the vertical input and horizontal accumulation. We can use the switches and input is applied in here, accumulate this horizontal way. We can just make it. So to make it, we have only the 4 switches and data path rearrangement. So the overhead is not that large. So then this computer memory can support this multiplication and this multiplication as well. So then we don't need the transpose operation, then we can speed up and we can increase the utilization. And so we designed the accelerator. And one other operation that we can speed up is actually the AV multiplication. Usually in the AV multiplication, I told you that the V matrix is coming from, on this transformer, the operation, the V matrix is generated in here. V matrix is generated and is multiplied by A, and the Z matrix is generated. So for the V matrix, actually the V matrix generation, because they are using this multiplication like this way, the V matrix comes out in the horizontal direction. But the problem here is when they do the AV multiplication, they're using this vertical direction, the multiplication. This is multiplied by this one. So because the output comes to the horizontal way, the problem is that we need to wait all the V matrix comes out, then we need to execute the AV multiplication. So this is also the waste of time. And also the WV matrix is not used. So using this, this is the utilization is going to be getting lowered. So our idea is how we can just make this V matrix come to the vertical way. Then we can use the transposed memory. So using this the V input and the V matrix, the multiplication, the V matrix comes to the horizontal way. So we can use this transposed memory. And it cannot be executed in the conventional way of computing. And after V comes in the vertical way, we can just do the computation to generate the Z matrix. So we used actually the ping pong architecture, ping pong buffer. So after is V generated, V is used to the AV multiplication. Then while they're computing the AV multiplication, this one is generate the output and store it on this lower buffer. Then it is a ping pong architecture. So we can improve the utilization and reduce the latency of this architecture. So overall, for the evaluation, the proposed transposable memory has only the 6% area overhead compared to the 10T conventional SRAM. And also compared to the transposed buffer, so the area overhead, area is going to be 60% smaller. So finally, we show that about faster, 2.8 times faster, the operation with the reduced latency about the significantly improved the reduced latency. Okay, so that's it for the computing memory architecture. So today I presented 2 topics, how we can reduce the computational complexity of these transformers and also how we can speed up and increase the utilization of this computing memory architecture. So yeah, that's it for my presentation. So I'm happy to answer the questions. Thank you.
Thank you, Jongsun. This is a very emerging topic.
Okay, thank you.
So,
yes.
Do you use synchronization techniques on your transformer architecture? How about the accuracy drop after compensation?
Oh, so you mean the compensation, meaning that the retraining?
INT8, INT4, or INT16, or the operation is floating point process, floating point operation.
Okay.
Your architecture.
Yeah, we have about, it depends on the data set. So we have about less than 1% the accuracy degradation is about. Yeah, this shows the accuracy degradation compared to the baseline. This distance shows the accuracy degradation compared to the baseline of floating point computation. Thank you.
Yeah, also in this slide, because you employ the clustering technique to kind of reduce the density of the attention maps.
Okay.
Yeah, the attention map. So that you can only process on about 15% of the centroid cluster. But you actually introduce kind of pre-processing phase. That is, you have to do the clustering. And after that, you have to do the cloning, okay, to reconstruct the
Yeah, right.
map. Okay. So these two are actually considered as the additional overhead. So besides the 1% accuracy calculations, in terms of the computing time, because you need these two actual computing overheads, okay, how about in terms of the computing latency compared with the original one?
Okay, so what is the number of clusters? The number of clusters we are using is actually different from the layers to layers. So it is going to be actually that kind of the number of clusters decision, and also how we can just group it, usually is decided in the O prime.
Okay.
Yeah, O prime, and after it is set, we can do only the inference operation. So using the many data set, consider the many data set, I mean, we use the setting in the O prime, and for different layers, we just decide which clusters we are going to use, and then that we can do the computation. So much of things can be decided offline. So
Okay.
it can be, I mean, yeah.
Okay, but you still need to perform clone process.
Yeah, right. Yeah.
Inference,
Yeah.
right?
So our idea is how we can just execute the computation is parallel to reduce the latency degradation. So this architecture reflect that feature. Yeah, thank you for the question.
Okay. Right, so if we don't have further questions, then thank you for
Okay, thank you for listening to my talk. Thank you.
Thank you.